It's a pleasure to have today for our morning tutorial, Steve Tobias, who has been a festival regular now since I think the second festival, as far as I can recall. And Steve's history is very simple. Trinity College, Cambridge, for both undergraduate and graduate, a brief sojourn in Colorado, then more Trinity College, Cambridge, and then University of Leeds, where he's professor of applied mathematics. And he's done a wide variety of things on convection and dynamos and various two-dimensional problems in beta plane MHD. And today he's going to tell us about better living through machine learning, right?
Kind of, yeah.
And it's the usual story of 50 minutes roughly, with short interruptions for clarification.
Yeah.
Okay.
Yeah, absolutely.
And then a longer, about a half-hour discussion at the end.
Okay, thanks, Pat. Okay, thank you. So I'd like to thank the organizers, especially Guillaume, for organizing a conference under such difficult circumstances. When Guillaume told me the title of the theme of the conference, as it were, I had two options. One is I could make my talk fit with the theme of the conference, or I could just do what I usually do and just talk about what I always talk about. And I actually managed to overcome the inertia that affects everybody. And so I wrote a talk from scratch about, which actually fitted into the theme of the conference. So, wrong way. No, okay, it's a good start. So which way advances it then? No, I'm confused.
It's this way. You see top advance.
Yeah. It's not advancing it. Okay,
It's not advanced.
I'll use
No,
this one.
The old-fashioned.
The old-fashioned.
The pointer still works.
The point is still okay. Great. So in order to come up with a talk from scratch, I'd like to really acknowledge the people who've done all the work. So I'm going to, the work has been mainly done that I'm going to present by Anton Pershing, who was a student at Leeds and has just finished working as a postdoc at Oxford with Tim Palmer. And the second part of the talk has been done by a current student, Alistair Roy, who's at Leeds. He's part of our Centre for Doctoral Training and the host of supervisors who supervise Alistair with me, including some supervisors who are at UK AEA. And then the final part of the talk, if I get time. If I don't get time, then don't worry about it, because Florence is going to be giving a whole talk on the methods that we use for this minimal seed bit of the talk. So let me start by giving an outline of the talk. So I'm going to give some motivation, and my motivations always seem to come from the same places, which is the Earth and the sun's magnetic field, so dynamo problems. And then perhaps I'm going to talk about probably two of these, maybe the first two, which are motivated, I would say, by these problems, but actually you'll see, as always, as I always do, I never quite solve these problems, nobody ever does. I try and look at problems which have a similar mathematical structure to try and understand something about how these things might work. So let me start just by doing some motivation. And so I'm going to talk a little bit about how planetary and planets and stars create their magnetic field. So we'll come to the physics in a little bit, but here's an interesting time series of the geomagnetic record. We know that the Earth's magnetic field at the minute is predominantly dipolar. It's fairly weak, but certainly weak for you guys. I mean, this is a fairly weak magnetic field. It's predominantly dipolar. Currently, the dipole axis is offset by about 10 degrees from the rotation axis, and I'm sure you all know that the Earth's magnetic field stays with a certain polarity for a long time scale, but it has a tendency to flip, okay? This is different to the sun. You'll see the sun's magnetic field flips every 11 or so years, but the Earth's magnetic field well, you can see the record here. You know, it may stay around for a few 100,000 years and then flip. You get these periods called chroms and superchroms where it stays in its current orientation for a long time. So one of the things, obviously, a dynamo model would want to explain is not just how we get the Earth's magnetic field of a dipolar field of about this strength. You'd also want to understand, you know, why it flips and how it flips. Okay. Now sometimes it doesn't quite manage to flip. So those are called reversals when it flips. Sometimes it doesn't quite manage to flip. It tries, but it doesn't quite manage it. And these are called excursions. So it's widely thought that these excursions are failed polarity reversals. So here are some pictures from this nice paper of where the axis of the dipole has been, and this is all taken from sedimentary records and paleomagnetic records. And you can see that sometimes the North Pole, let's say, takes a massive excursion, but then it comes back round and settles back down to being North Pole again. So it looks like it wants to reverse. So the North Pole does kind of make it down there, but it doesn't quite manage it. So excursions are kind of, well, technically speaking, if the Earth's magnetic pole wanders 45 degrees or more from the rotational pole, that's called an excursion. And they're generally attributed, although I think this is just a story rather than a theory, let's put it that way, to the fact that the Earth's magnetic field has somehow managed to reverse in its fluid outer core, but it hasn't quite managed to reverse the field in the solid inner core. And because that field has kind of stayed where it is, it doesn't quite manage it, and you stay with the same polarity. Whereas for a full reversal, you reverse the field both in the fluid outer core and the solid inner core. So, okay, so that's the Earth, and I'll come back to that in a minute. The other motivation comes from the sun. And so these are very beautiful pictures from this lovely paper.
Sorry, I'm going to bother you.
Yeah.
There's the wrong sharing on Zoom. Apologies for that.
Okay.
So I hate this thing.
I hate this thing.
Okay, that should do it.
Sorry. Okay, so we need to get rid of.
Yeah, now we need to get rid of that. Apologies.
That's okay, don't worry. So usually when I'm showing historical observations of the sun, I show Galileo sunspot drawings, but I thought I would diverge this time. So these are sunspot drawings by Hevelius, and both of these pictures are in this very nice paper in Nature Astronomy, recent paper, looking at the historical record of the sun's magnetic field. So as we'll see, sunspots are manifestations of the sun's underlying magnetic field. They come and go with an 11-year cycle. They're dark because the magnetic field that you see in a sunspot inhibits the convection that's happening there. So they're still really bright. I mean, if you put them in the sky without the sun behind it, they'd be about as bright as the moon, but they're relative to the rest of the sun, they're dark, and their sites a very strong magnetic field. So if you're interested in the structure of sunspots, then you might be interested in the interaction of magnetic fields with convection, very strong magnetic fields with convection. And one of the problems I'm going to look at is a very simple version of that interaction. If you take the solar record, you see that sunspots come and go with an 11-year period. This is the solar cycle. This looks blurred, and it is blurred because this is the amalgamation of lots of different definitions of what's called the sunspot number. They call it the blended group number. So you can get cleaner versions of this, but I just wanted to show you that the 11-year solar cycle comes and goes. It's modulated on a long time scale. And this is where Galileo started observing sunspots, and then the various people observing. You can see interesting dynamics. So in the 17th century, there was this period called the Maunder minimum when sunspots switched off. When sunspots re-established themselves, they came only in the southern hemisphere of the sun. So this is some indication of the breaking of symmetry, or the interaction between dipole and quadrupole modes, if you like. There are periods where sunspots appeared at the equator. You can see here in the 18th century. This is an example of a quadrupole mode taking over from the dipole mode. But recently, the sun has been pretty much predominantly dipolar. You can see here. And you get the famous butterfly diagram where sunspots start off at mid-latitudes and migrate towards the equator on a roughly 11-year timescale. That's the thing that causes the solar cycle. And then the sunspots die out at the equator and then come back again at mid-latitudes. And there's a lot of interest in trying to predict, future cycles, because of course the sun's magnetic field has an effect on, say, orbital drag of satellites and various other important terrestrial effects, such as, solar flares are very important, and that they correlate very well with the solar cycle. What you can see here is that there is some kind of large-scale mode that's interacting with very turbulent behavior. So you might want to try and get a reduced model of the behavior of the solar dynamo. There is a significant large-scale mode here that's definitely occurring with a kind of period of 11 years, and the interaction between dipoles and quadrupoles is clearly important too. I'm not going to talk too much about getting reduced models of the solar cycle. I will talk a little bit about getting reduced models of the interaction of convection and magnetic fields. Okay, so one of the things I'm interested in looking at is combining physics and data. Now, the moral of this story, the moral of the talk is you really need to understand the physics. You can't get everywhere. There are some people who think you can just get everywhere just by looking at data. Data can tell you certain amounts of things, especially in astrophysics, or even in geophysics, we don't have a lot of data. So you're never going to get anywhere just by looking at the data. However, the other extreme position is where I just ignore the fact that I have some data, which is what I like to do for 20 years or so, is possibly not sustainable either. So I think combining the physics and the data is a good thing to do. So you might know that the equations should take a certain form. You might know that the symmetries of the equations have to take a certain form, or you might know that interactions, for example, your nonlinearities may be energy preserving. If you know all of this stuff, then you should take account of this when you're doing your data. And if you combine the two, the idea is that somehow you can improve your model. And I've just put here two very nice examples of where understanding the physics and the data enables you to make a lot of progress, one of which I think you might hear about next week by Pat's former student, Robin Heinonen. So I won't say very much about that. And then there's a nice example in the plasma physics community by these guys, Alves and Pusa, where essentially they managed to derive, what did they manage to derive? They managed to derive a set of PDEs from a PIC calculation and then tested it against the theory, which was a nice thing to do using one of the techniques I'm going to talk about. Okay, so let's come back to the Earth. What we're going to be interested in is dynamo action. And the Earth has this form where we have the crust and then the slowly convecting mantle. From the point of view of the dynamo, it's so slowly convecting that we may as well model it as a solid. We think most of the dynamo, or all the dynamo action, is going to take place in the fluid outer core of the Earth. And then there's a solid inner core, and convection is driven by the freezing out of light elements at the core, inner core, fluid outer core boundary. So the equations for this are known. We just can't solve them. I mean, it's one of these ones where the parameter regime is so extreme that we can't solve the equations. And the reason, as with all of these things, is that the ratio of timescales that you're looking at, and spatial scales, but predominantly for the timescales, is so vast that the non-dimensional numbers that you look at, which measures the ratio of timescales, is impossible to simulate on a computer. So, for example, the Ekman number, which measures the influence of rotation versus viscous effects in the Earth, in the fluid outer core, is of the order of 10 to the minus 15. And there's simply no way we can put something like that on a computer and solve it. That doesn't stop people trying to do this. I mean, here are the equations. And of course, some of these are heroic efforts. So this is the latest, I would say, state-of-the-art model of convection in a spherical shell. This is courtesy of Julien Aubert, where he solves the relevant equations. He solves the momentum equations. This is either the temperature equation, you can think of it, or the equation for the concentration of light elements, together with the induction equation. So you've got thermally driven or compositionally driven convection, which drives a flow, and that flow through here can generate a magnetic field, and the magnetic field can act back on the flow. The key thing to note is that the Earth is rapidly rotating, so some of these terms are more important than the others. So the Coriolis force is going to prove to be very important. Inertia is going to prove to be not very important at all. Pressure is always important in some sense. We need to somehow drive the flow, so thermal driving is important. And the importance of the magnetic field, whether it enters into the leading order balance, is a somewhat controversial issue, as I'll come to. But let's imagine it pretty much does, for reasons I'll come into. So it does enter into the leading order balance. And then viscosity, as I've just said, is of order 10 to the 15 times smaller than the Coriolis force. And so you might try and understand the evolution of the Earth's magnetic field by solving the induction equation together with an equation where you kind of balance the Coriolis force, the pressure, and the Lorentz force. And that's called magnetostrophic balance. A question is, how big is the magnetic field? And one of the important things that I'd like to get across to you about the Earth's magnetic field, as opposed to, say, the sun's magnetic field, is that we believe that the magnetic field plays a key role in releasing constraints on the fluid to enable the fluid to flow to generate the magnetic field in the first place. So it's a kind of essentially nonlinear effect. If the magnetic field gets big enough, it allows you to have a more efficient mode of convection, which in itself allows the magnetic field to be big enough. So it's a kind of bootstrapping effect of a finite amplitude magnetic field that you couldn't see, or you wouldn't see by doing, say, linear theory, a linear dynamo theory. Okay. So these are, again, this is the computational tour de force. This is the what can be done with computational dynamos. Using massive computers, you can maybe get to Ekman numbers of 10 to the minus 7. If you push it hard, remember the real value is 10 to the minus 15. So although these are impressive, they're nowhere near the correct parameter regime. What you see, though, is a tendency for the flow to line up in a line with the rotation axis, you can see here. And this is evidence of what's called the Taylor-Proudman theorem, where one's balancing the Coriolis force with rotation. Okay.
What is modeled here is just the inner, the solid core, and the fluid.
Yeah, and because the mantle is essentially on the timescales you're interested in, not moving, so you model it as a solid insulator. Okay, so you can't quite see what it says here, but it says what happens, and there's a good theory which goes behind this. If you do linear theory of a rotating magnetized fluid, what you find is that the magnetic field can break the constraints that comes from rotation. So here is the critical Rayleigh number at which convection sets in as I increase the magnetic field strength, okay? And this is taken from the book of Moffat and Dormy, who replotted some of these famous diagrams. This one's from David Fern. And so what you see is that the critical Rayleigh number, i.e. the Rayleigh number at which convection sets in, if there's no magnetic field, remember the Ekman number is tiny, right? It's 10 to the minus 15. Convection does not set in until the Rayleigh number gets to the order of e to the minus a third. So this is a very large Rayleigh number is needed to drive the convection. And that's because rotation tends to want to make things line up with the rotation axis. And that's not a very efficient way of getting heat out in a calculation. But I'll come to this end. If the magnetic field is very, very strong, then that also inhibits convection. But the interesting thing is that there's a sweet spot here in the middle, where if the so-called Elsasser number, which is a measure of the competition between magnetic field and rotation, is of order 1, then you can get convection setting in at kind of order 1 Rayleigh numbers. Okay, so if Ekman number's 10 to the minus 15, this is about 10 to the 5, and this is order 1. So the argument goes, and this is an argument due to Paul Roberts going back into the 1970s, is that there are 2 branches, okay, for dynamo action. There's a so-called weak field branch here, and the weak field branch is, we go along here and convection sets in. Convection sets in at a very high Rayleigh number, so we're kind of here, and that drives a dynamo. And that dynamo has a very weak field and exists happily along here, but it's not really what we're seeing. What we're seeing is this strong field branch whereby the magnetic field has grown to some amplitude here. It's grown to some amplitude, and the amplitude is just that amplitude which makes the convection really efficient. And this is called the strong field branch. To get from here to here, you've turned a linear theory into a kind of non-linear theory. So that's where all the argument comes about as to whether this is a reasonable thing to do, but it does seem like a very plausible argument. And then you would say, well, if I have this strong field branch and I've managed to get to here, then this strong field branch may exist all the way back down to some Rayleigh number well below the convective onset. Yeah, you have this hysteresis and you have this incredibly strongly subcritical dynamo branch. And these types of dynamos are called essentially nonlinear dynamos because you need a nonlinear, they're driven by the Lorentz force. Here the Lorentz force breaks a constraint. In other examples, which I think Florence will talk about, they may allow instabilities to occur that can't happen if you don't have a finite amplitude. So there are other dynamos which are of this type, and Florence is probably going to talk about those after coffee, right? Is that right? Yeah. So if you have these essentially nonlinear dynamos, what do you have? Well, you have this is a kind of phase plane.
Could I bug you?
You can, yeah.
Your previous slide there.
Yeah. So I
You
just
have different dynamos listed.
yeah.
I mean, but the MRI is a very, wonderfully convenient linear instability. I don't really see where the S curve comes from.
Okay, so the instability exists at arbitrarily small magnetic field, but you need the turbulence that is generated by the instability to be strong enough to sustain the dynamo, the magnetic field that you first thought of. And that is, with finite dissipation and in a finite geometry, you do need a finite amplitude magnetic field to get the dynamo.
But I mean, it's in some sense, it's just set by the dissipation. I think I wouldn't call that a nonlinear process. I mean, you just need a certain amount of.
You need a strong enough magnetic field
strong
to get
enough
you,
field to
essentially, to get you over this branch to here. As
But
it
is
were.
it really a change in branch or just beating dissipation?
Maybe Florence will say something, but I would imagine if you impose a strong field on a dynamo, an accretion disk dynamo situation, you would see this hysteresis. So you could go back and get dynamo action for, yeah. So, I mean, this is just a kind of phase plane analysis. So you might think you have a weak field dynamo down here, or perhaps no dynamo. And the idea is that, if you start off somewhere If these two are coexisting, hysteresis, you might have a turbulent trajectory, which comes back down here. You might cross this thing, which is called the edge of chaos. These dynamical systems people, they have some good names. So if you cross what's called the edge of chaos, you can jump from your trivial solution, if you like, which could be the weak field dynamo, it could be no dynamo whatsoever, into the regime where you get this strong field dynamo. And there's going to be some energy, at which a minimum energy configuration, which gets you from here to here. And what you'd like to know is what is that state that gets you, and that will help you find subcritical dynamos. This diagram is taken from, what's it taken from? It's taken from a paper on transition. I just changed the words, laminar state to turbulent state. And you'll see that the subcritical dynamos have a lot in common with transition in pipe flows. Okay, so that's motivation, which was meant to last 5 minutes. I'm now 27 minutes in, so that's good. Okay, so I mentioned transition, and I'm sure you're all aware of Reynolds' experiment of pipe flow. So you know that if you increase the flow rate down a pipe, you can go from laminar flow, you can go to turbulent flow. And the key thing of interest is that you can do this even when linear stability analysis tells you that this laminar flow should be stable. And so it has this very similar characteristics to the problem that I just talked about. So these are very famous subcritical transitional flows. There's plain Couette flow, which is the one I'm going to talk about, pipe flow, which was the one Reynolds did, and plain Poisson flow. They have slightly different characteristics in that these two, they're linearly stable at all Reynolds numbers, but you find you get sustained turbulence in this parameter regime. Plain Poisson flow, there is a linearly unstable linear instability, but again, you get Reynolds numbers way below where the linear instability occurs. So it has a very similar characteristic in the sense that you have regimes where you have coexistence of a laminar state with a turbulent state. And you have this, if you think about this as the edge of chaos, as it were, if you somehow go from one side to the other, then you'll be attracted to that state rather than this state. Down here, you may hang around this, this state for a long time, but eventually you will have to go back to this state because this state up here, you know, it doesn't really exist. There's only a shadow state there. Okay, so what do I mean by plain Couette flow? I'm sure you've all seen this before. You take the Navier-Stokes equations along with it's the incompressible Navier-Stokes equations. You either do an experiment or you solve it on the computer. So you move one wall this way, one wall this way. You set up a shear flow of this form, a linear shear flow. And this shear flow is not unstable. There is no linear instability, but again, you can find turbulence going for Reynolds numbers much smaller than, well, than infinity, much smaller than infinity because it's never unstable. And again, so again, this is just the same picture, but now I put in the laminar state is here, turbulence is up here, and you might want to find the minimal C, the thing of least energy, which will take you from here to here. Or you might want to try and predict when you're going to get a turbulent state from a laminar state. And so this is where the first part of my talk comes in, is can data tell you that you're going to go from a turbulent state to a laminar state, or vice versa? So those of you who were here 3 years ago will possibly remember Ed Ott's beautiful talk on what he called reservoir learning. And he talked about some various models where he did some reservoir learning. And what he managed to do was predict the evolution of, well, various states. He did the Kuramoto-Savashinsky equation here. So this was the true state. He did some learning on this true state. And this was the prediction. And what he showed which was kind of amazing to me, was that you could then, this was a faithful prediction of the true state for about 5 Lyapunov times of the turbulence. This is pretty good. This is pretty good for a chaotic state to be able to predict for 5 Lyapunov times. I thought was pretty impressive. And so this got me interested in these methods, these reservoir learning methods, and to try and see how they work, because they're a particular type of learning. Okay, I'm not going to go into too many details, but the particular form of reservoir computing that Anton was interested in with these echo state networks, and they're different to these recurrent neural networks. They're a lot simpler than lots and lots of people play around with, and they're a lot quicker. Yeah. Can you speak up?
You're talking about nonlinear diagonals.
Yeah.
Yet you seem to be extremely happy that 5 Lyapunov times is already a good achievement.
Yeah.
Bridge that gap.
Okay. I'll come back to that, because for a chaotic system, you're never really going to be able to predict better than that. But you may be able to say something else. Yeah. I mean, even if you had the proper model and you changed the initial condition very, very slightly, you might get to like 4 or 5 Lyapunov times where these two shadow each other. So it's kind of difficult to do much better than that. But you might be able to say something else, which is what I'm going to come to. So this is, okay, I'm not going to go too much into the details. I can talk about this, in the, what's it called, tutorial later on. Instead of having these recurrent neural nets and doing a horrible nonlinear optimization problem, what you do is you have this kind of reservoir of nodes. This reservoir of nodes is wired randomly. So you just wire it randomly. You connect nodes to other nodes randomly. And you have this input to the system. And the only thing you're going to be able to play around with is the output. So you then take the output from these nodes, and I'm going to play around with this bit, but I'm going to leave all this bit the same. And this makes training a linear problem rather than a nonlinear problem, as you'll see. And that means you don't have to spend days and days and days training your network. You can just go solve a linear problem and do it. I don't really have time to go into it. But essentially what you do is you feed in some data. Let me just go back. You feed in some data here from the time series that you have. It passes through here, and then you take note of all the answers you get when you've got to here. Okay. And then what you want to do is you want to somehow configure the W outs such that this compares very well with the true answer, as it were. And so this really is a linear problem. So you're minimizing this for W out. And so you can just do this using a more Penrose pseudo inverse, if you like, or for bigger problems, you can do iterative methods. It doesn't really matter. And so what you then do when you do your training is you've got these solutions for W out. Okay. Fair enough. And then you say, okay, now I just run it on, and instead of just taking things here and trying to minimize something, I take my output and I just feed it back in. So I'm taking the reservoir, the echo state network, as a dynamical system. Okay. And I'll see how well this can predict things going forward. And Ed showed that it can predict pretty well. Okay, I won't say much about that. But because this is a linear, in a sense, you're solving a linear problem, you might be able to try and do some theory behind it. And so there's this thing called the approximation theorem. And somehow the reference has dropped off, but I can give the reference to anybody who knows it. Which says that an echo state network can be expected to embed trajectories of the true system via this theorem. And I was kind of surprised at what that meant. I mean, if it really does embed trajectories of the true system, then it's not really just a fast fitter of the attractor. It's somehow encoding something more about the attractor. So we asked the question, can it predict dynamics or statistics it's never seen? So we go back to plain Couette flow, and we're too scared to take the full Couette flow model. So we took this model called the Moelis fast Eckart model for Couette flow. All this is a Galerkin truncation of the true model. So you get 9, you truncate, you project onto 9 modes. So you get 9 ordinary differential equations. And so these are typical evolutions of the 9 variables corresponding to the different components of the velocity. And we're going to use this as a model for, well, both the Couette flow and the geodynamo, actually. And we know that you get, in this model, you get sustained turbulence, meaning that these things don't laminarize for Reynolds number greater than or equal to 320. So we're going to look below 320 and above 320. So what might you expect to happen? Well, below 320, these things will bounce around. They'll do things like this and bounce around and bounce around. And then eventually they'll go to 0 because you're below sustained turbulence. Above 320, they'll bounce around and bounce around continuously. And you might want to know if I give it something of a perturbation of a certain amplitude, will I go to turbulence or will I go to the laminar state? So here are some examples for Reynolds number 300, and these things laminarize. And they laminarize because the turbulence in shear flows from the dynamical systems point of view can be thought of as what's called a leaky attractor, meaning they get kind of bounce around the attractor for a while, but then eventually they find a hole in the attractor and they go to some other state. And in this case, the state is the laminar state. If this was the geodynamo, you might think about this if you went to this side of the saddle mode bifurcation, you might think of it bouncing around the strong field dynamo for a bit, but then it couldn't sustain it, so then it might go back to being no dynamo. Okay, so these are things at different, just different realizations of the same run, and you can see that sometimes they abort. They look like they're going to laminarize, but they don't. They come back again. Sometimes they spend an awful lot of time not looking like they're going to laminarize, but eventually they do. And you might want to know what is the distribution of this waiting times. That's something you might want to know, even if you can't predict exactly when it's going to laminarize. So what did we do? Well, for training, we only consider turbulent trajectories without laminarization events. So these are different Reynolds numbers. So you kind of train it on the bit where it's bouncing around. Here we go, bouncing around, etc. This one is going to Reynolds number 500. I guess it's sustained turbulence, so it keeps bouncing around. So we consider only turbulent trajectories without laminarization events and train on those trajectories. And then we say, can this thing work out that it's going to laminarize? Okay, this one actually did laminarize even though it's above the, so we must have been a bit unlucky with the initial condition. Okay, so of course, all of these do eventually laminarize. So the question is, can we predict that this is going to happen? So, well, short-term prediction, it does about as well as you might expect. So this is what Brienne was saying. You can predict for essentially 5 Lyapunov times forward. So as I've said here, as in Hedot's paper, the ESN can only predict a few Lyapunov times ahead, which is not bad, actually. But what amazed us, or amazed me, is that this is the true trajectory here, going off to this laminar state. When we did prediction using the echo state network, it managed to learn that it was a leaky attractor and would go to some state. Remember, it has no idea what this state is. It just has no idea. So it went to the wrong state, but it still learned that it went to some different state.
What do you mean that it is able to learn? Because if you didn't teach,
Oh, okay. So it's managed.
it's able to find it by itself.
Yeah.
He's not the learning, he's a discoverer.
Okay. Yeah, okay, yeah, maybe that's a better word for it. It's a discovery. It's managed to somehow find something out about the attractor from seeing one part of the attractor, never having seen that bit of the attractor, which is the crucial bit. But what is key, and it's probably clear.
The figure you showed before, there were phases, relatively long phases, which were looking like. So you just have that.
So these things. Okay.
Or you can do that.
Yeah, I'll come to that. I mean, this is why I spent a long time talking about reversals and excursions. You probably say. So these are, if you like, these are failed laminarization events, if you like, rather like an excursion is a failed reversal. And to give you the punchline, if you do not include any of these in your training data, it's not magic. It's not magic. It can't do it. So someone is learning something about the transverse properties of the attractor from these events. Okay, that's good. But what was interesting to us is that, okay, what am I showing here? I'm showing these lifetimes. So the distribution of the lifetimes at different Reynolds numbers. The light figures are from the actual MOLIS model. The dark ones are from the echo state network, which I should say runs, thousands of times faster than even the ODEs, and it would run an awful lot quicker than the PDEs. These are the distributions of weight, sometimes called waiting times. It's just the time for laminar to laminarization at different Reynolds numbers. And so we put on here our failures in terms of, as well as our successes. So the dark colors hasn't come out quite so well, are from the true system. The light colors are from the echo state network. And you see as a distribution, you get a pretty good approximation of the waiting time distribution for these three Reynolds numbers. Okay. This is Reynolds number 200, doesn't work at all. And that's because we don't have long enough training sets. This thing laminarizes almost immediately. So we just can't train it long enough to do this one. This one is the one for sustained turbulence. And again, we couldn't, there was no way we could get anything to fit this distribution. I mean, in the sense, you can go to infinitely long waiting times. Okay, so as I've said here, and as Xavier referred to, you need to guarantee that the training time series includes excursion, well, not close to the laminar state, but away from the turbulent state. So we can get the distribution right, but you do need to have some of these, if you like, warnings that it might happen. The other thing we checked, which is is whether can an echo state network be used as an early warning system, in the sense that if you're coming along to this thing, this event here, can you work out whether it's going to laminarize or come back, as it were? And we worked out that you can only really do that if you get fairly close. So it can be used as an early warning system, but it's not, I wouldn't necessarily rely on it. Okay, so the next thing to try with this is, that was a fairly simplified system. The next thing to try with this is bursting. So bursting is, again, you have a kind of turbulent state, or one state, and then another state. So here it is bouncing around. This is so-called Riddle basin of attraction in coupled Fitzhugh-Nagumo units, but it's a great example of something where you have one type of behavior, then an excursion, and back again to this kind of behavior. So the next thing we're going to try is to see whether you can do anything with this. And this is very reminiscent of convective bursting. So this is bursting going back to 1983. The kind of bursting you get where you might generate shear flows in convection. So again, those are interesting things to try. How am I doing for time, Pat? Okay, so I'll probably just do this, and then anything else I can talk about this afternoon. Okay. Okay, any questions about that whilst I'm having a drink?
One question. So the machine learning technique that you used in the reservoir one,
Yeah.
What is the main difference with the conventional layer one? And why this is better for your work?
Okay. In a sense, it's not better. In a sense, it does as well, but it does well using a linear fitting. Whereas when you do the current neural nets, you have to solve a horribly complicated nonlinear because you kind of rewire or reweight all of the weights each time. And that's a very difficult thing to do. All I have to do is find the inverse or find a pseudo inverse of a well, not I, Anton has to do is find the pseudo inverse of the matrix. So it's very quick. The training doesn't take very much time as well.
Okay.
David?
For example, you have one stage coach.
Yeah.
And more complex systems maybe on that end. So are you somehow assuming that you're close to some kind of critical boundary in a system that is like just beyond some modification point where you expect only to have one outcome? Or two outcomes,
Yeah, I mean, I guess, yeah, that's right. You're assuming that if it doesn't go to the turbulent state, it goes to the laminar state. If it could go to one of two different states, then I guess that'd be an interesting thing to look at. And in fact, some of these problems actually, I mean, you can do things with symmetries, so it could go one side of the attractor or of the hyperbolic point or the other side. And those would be interesting. My feeling is, how is it going to be able to tell unless you give it the training that it goes, it's trained such that you give it that bit of the trajectory, but it's worth looking at certainly. Yeah. Dominic, do you have a question?
You need to teach the system that goes toward must be from the front. And so I would like now to know what kind of can you
It's a really good question. The answer is we don't know.
Guillaume, could we get the speaker to repeat the questions, please? We can't hear the questions, at least a short version.
Yeah, okay. So I'll try and repeat that question. Dominique, you're asking, you need to know something about, in that case, the excursions to get the fact that it goes to the lambda state. And that's not true of all systems that do that. So what kind of systems might this work for? So this is why we're looking at this next. This kind of bursting behavior is often put down to what's called a riddle basin of attraction. So that means you have an attractor and it's doing something like this, okay, in some subspace. And then at some points on the attractor, there are points where you become unstable transverse to that subspace. So you kind of shoot out of that subspace. And so I think it will work well for that because you're learning something about the dynamics kind of close to the attractor, as it were, by being close to the attractor, if you see what I'm saying. So if you have the attractor, if you have an attractor which looks like this, it's very complicated, but there's some bit over here where you get kind of thrown out, kind of transverse, and then maybe you get injected back in, which is what we're kind of seeing there. Is if you learn that you nearly get thrown out a little bit there, then that's the kind of thing that might work. Other things, I guess, we just have to try.
But it looks like more cumbersome version of the Shimikov structure where currently you get the feeling that there is an attractor and some moment the system feels there is one stable direction, it makes without excursion and comes back. So
Yeah, that's exactly right. The Shildikov attractor would be a great example of this kind of dynamic. Okay, so the second part of my talk is really to do with, this is the work that Alistair Roy has been doing. And there's a question of whether given a data set, can you work out what are the ODEs or the PDEs that describe that data. And so I don't have as much time to go into details, but this is a subject of quite intensive research. And there's various different ways of doing it. The way I'm going to look at is called SIMD, it's Sparse Identification of Nonlinear Dynamics. And it's a method put forward by Steve Brunton and Nathan Cutts at the University of Washington. And it's a very, very simple idea. And the cleverness comes in essentially doing it efficiently, as with all of these things. Now I've walked around and I've put my... Okay, so imagine we have a dynamical system that we all know and love. So here's the Lorentz system, okay? This is derived from convection for those people who don't know, but this is the famous attractor at rho is 28. We have this data, and the question then is, if I know just this data, can I get these equations back? Okay, so it's an interesting question. And so, well, okay, imagine that I can take this data and I can work out not just X, Y, and Z, so I have the data for X, Y, and Z, but I can work out X dot, Y dot, and Z dot. Now, for true data coming from, say, an experiment, this is likely to be very noisy. And so working out derivatives with respect to time is likely to be an interesting question, and so people have looked into that. But let's imagine we have clean data, not noisy data at all. And so we can work out X dot, Y dot, and Z dot. Of course, if you only have a finite amount of data, so you don't have the regular, spaced, fine enough cadence, then that also might cause trouble as well. But let's imagine we can work out X dot, Y dot, Z dot. Then all I can do to try and work out what the equations are, I can just try things. I'll just try things. I'll just imagine I'm going to try things on the right-hand side. I'm going to try functions from a well-known, from a library of my choosing. And this is really coming down to the fact that certain nonlinearities occur in physics. I think it's fair to say, and certain ones don't. And so you just choose what you think might be a plausible library. And this, I'll come back to how you might do that. But the first thing you might do for an ODE is put in linear terms, put in nonlinear terms, and just see what happens. Okay, and then you have X dot, Y dot, Z dot. You can work out, let me just go ahead. So you have X dot, Y dot, Z dot, and then I might choose my library to include like constants, X, Y, Z, X squared, X, Y, X, Z, blah, 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 all the way up to, I don't know, Z to the 5th. If I was feeling particularly energetic. So I've now got X dot, I've got my candidate library thing, and then I'm linearly regressing just to find these coefficients. And the point is, the hope is that this is sparse, okay? And what you use is methods that promote sparsity to try and get these coefficients. So you kind of regress this against this, and you get out the coefficients, and if they're 0, then it should give you 0. Okay, so you can put in as many as you like. Of course, you're making yourself a hard problem, but the idea is that there's a sparse coefficient for the dynamics, and then this gives you out your model. So the question is, how well does this work on a more? But the Lorentz equations, it's been shown to work incredibly well, even with noise, even with limited data. So how does this work on a problem, a PDE problem? So we're going to do a very classic problem, which was motivated by the sunspot dynamics. It's about as simple a problem as you can get. We're going to do 2D magnetoconvection. Because it's 2D, you can write the velocity as the gradient of a stream function, and the magnetic field you can write as the gradient of a vector potential. And you derive equations, which I'm not going to go into, for the A, vector potential, the temperature, so you have a hot plate here, bottom cold plate here, and the vorticity. And this is what relates the stream function to the vorticity. So which you can just solve those PDEs. Now, I'm going to try and get a reduced model. Now, a reduced model for this system already exists, and this reduced model is based on knowing what the linear eigenfunctions for the system looks like. That seems like a very sensible thing to look at close to onset, right? Close to onset, things look a bit like the linear eigenfunctions. So for the weak field branch of the geodynamo, that would be a sensible thing to do to get a reduced model. And so these are this is expanding, if you like, in the linear eigenfunctions, and you derive a set of equations. In this case, it's a set of fifth order ordinary differential equations for the coefficient of the stream function. You keep 2 for the temperature. So if you just went this far and didn't include the magnetic fields, you would get the Lorentz equations. But because you've included the magnetic field, then you get some nonlinear interactions, and this is the magnetic field acting back on the stream function, for example, by the Lorentz force. And this is a nice reduced model that occurs very close to onset. And so this goes back over 40 years to Knobloch, Weiss, and Costa. Question then is, but is this linear behavior? I mean, sorry, is this truncation relevant for strongly nonlinear systems? We know that the Lorentz equations, the PDEs rapidly diverge from the simplified ODE system. And if this is not relevant, can you do better using CGP? So what we do is, well, we'd quite like to get a reduced model. So we use something which turns PDEs, if you like, into ODEs. So, so to generate a reduced model, we just do a singular value decomposition of the data. So we have the data for the PDEs, and we want to find the amplitudes of modes. So these are going to be the SVD modes, the singular value decomposition modes. This is a standard technique. Okay, so we get these the singular value decomposition from the data, and then we try and work out from the amplitudes of those modes what do the equations look like. So this is the singular value decomposition. This is an example from where the solution is particularly simple. So what we do is we work out the amplitudes of the SVD modes, and actually this is very close to onset. So we would expect to find the modes that you see in the Knobloch et al. Model, and indeed we do. We find that you can pick 1 mode for psi, you might want to pick 2 modes for t, 2 modes for a. This is how much power they have. Okay, and so we checked, and these SVD modes are exactly the modes, the linear eigenfunction modes. What's interesting? Yeah.
We jumped from SVD to POD.
Ah, sorry, they're the same. And sometimes they're called EOF, just to confuse the issue. Apologies. I'm going to use them interchangeably as I can. So yeah, the SVD modes are sometimes called proper orthonormal decomposition modes, and the other lot, the climate scientists call them empirical orthogonal functions or something. Yeah, sorry, apologies. Yeah, thank you. And so these modes, they just oscillate around. So these are the periodic solutions. And now we might think, okay, can we get the model back from this? And the answer is no. We can't get the model back from this. It took us a while. I mean, it's obvious in hindsight. There are loads of models which will fit this. I mean, we could just say it's a simple harmonic oscillator, it will fit this. And so there's a degeneracy for dynamics, which is too simple. There is a degeneracy in getting back the model from the data. It's kind of obvious in hindsight that that this would happen. So, you know, there are various models. This was the Knobloch system. I think this is, you know, the one, but, you know, other possible models fit the data just as well. So it's just a warning that when the data that you get is too simple, then there's a multiplicity of models that will fit the data. So there's not enough information to distinguish between the two models. However, when you think about it, when you get a very chaotic system, which is doing something like this, rather than something like that, you think, well, it's not going to be very many models that fit something like that, hopefully. So let's see how well it does on the chaotic system. So For the POD system, for the chaotic solutions, interestingly, only 4 modes were needed to reproduce the behavior of the full system. Again, we can predict, if we take the model, here's the model we got out, okay, for whatever it's worth, and use it to predict forward. We can predict for a few Lyapunov times, which again, is not too bad. But I think the reason I think that this is nice, getting out the model is nice, is because you can really see where the interactions are. And this goes back to the work that Robin and Heinen and Pat did. It's like when you can see what terms matter in the model, then you can go back and really understand the physics. There's no point in doing all this and then saying this is a model, isn't it great? We really need to go back and understand the physics. So how well does it actually do? Well, it does very well. If you train it for long enough, you can get the symmetry of the solutions. So these solutions have to respect certain symmetries. So if the training data is long enough, so the blue is from the actual ODEs, the red is from the new model, and we're trying to establish whether it satisfies certain symmetries. So if the training data is long enough, then the symmetries for the underlying model will just emerge because you have enough data. However, if the data is not long enough and the physics tells you the symmetry, for example, A goes to minus A is the symmetry, then of course you can just put that into the model. You don't have terms which don't respect that symmetry, so that's nice. So you should impose this in your library of functions. Similarly, if you know something like the fact that the nonlinear terms are energy preserving, then you can impose that as a constraint. So again, you're solving these models by essentially minimizing some function subject to constraints. So if you have this as a constraint, then it can be imposed.
Have any of these games been played where the model exhibited different symmetries in different states? And it got it right, this, though, got it right. Because I can tell you, in the thing we did, it was a, well, it's, you know, it's a Hasegawa Wakatani.
Yeah.
First of all, if it's any system you know the answer to, that's one of them.
Yeah.
Secondly, it worked in the regime where the zonal flow dominated. So it became effectively one-dimensional in anything that mattered.
Yeah.
The minute you go to even a 2D regime, the machine learning thing crapped out.
Right. So
was unable to deal with, for example, vortex formation.
Right. So this actually is quite impressive. It's managed to do something for flow past the cylinder. So flow past the cylinder, I mean, that there is, there's a certain underlying symmetry of the equations.
Sure.
But then you know that you can get these vortices shedding
different
with
regimes
different,
of that?
yeah. And so it has managed to, well, of course, in a sense, you're taking some of that from taking the POD mode of the PDE. But it can't, yeah, it can. I mean, some quite complicated problems it can work. Okay, and then you might say, well, okay, this is quite a, sorry, let me just go back. This is quite a chaotic solution. You can see here, it's quite a chaotic solution. Again, coming back to Graham's point, you can't predict that far in advance, but maybe you might want to know the statistics of the solution. So there's various ways of measuring the statistics for this problem. You could work out waiting times or times to switch. You could work out PDFs of amplitudes of various other variables. The way these guys like to do it for kind of Lorenz type systems is to plot maps of, let me just say, plot maps of where the next maximum occurs in relation to maximum before. So you plot the amplitude of one maximum against the amplitude of the next maximum, and you get a map. And so here we're taking this map from both the POD series and the identified model, and they match really well. And just to show you here is, if you take the Knobloch model out of its regime of validity, it still doesn't do badly, but it certainly doesn't do as well as the Cindy model. So obviously this model is much better. There's more in it, so it's got to be much better than it was before. So just to finish, and I think I'll probably just finish there and So the summary of Cindy is that you can discover new simple reduced models, but it requires a good choice of basis functions. How do you choose your basis functions? Well, if you know something about the PDE, about the physics of the PDE, that helps. But there is now some papers on getting neural nets or getting some kind of data analysis to choose your basis functions for you. So any knowledge you have of the physics should be put in. I think this paper is very nice and should be interesting to you guys. They really took solutions from a PIC code and then essentially derived, if you like, averaged equations for the PDE equations for the evolution. And the nice thing, and I think this is something that we're looking into now, is going back to my motivation, is we'd like to get reduced models for something that's miles away from the linear instability. So not really on the weak field branch down here, something on the strong field branch. So can we find a reduced order model for the strong field branch of solutions, from the data? And that's something that my Marie Curie fellow at Leeds, Anna Gasseva, is looking into, along with some of these French guys, to take some of their strong field dynamos and then to try and work out a reduced model for the dynamics on that system. Okay, so just to say, wait for after coffee. Florence is going to talk about finding some critical states with the smallest perturbation possible. I might just say one thing about apologies about this, because I think this is quite interesting. So what's the idea? The idea before, we had a dynamical system and we ran it and we trained it and we thought, can we predict going further forward? Or can we say something about the statistics? The question is, there are some things that we can do computationally and some things we can't. So I said we can't solve the geodynamo because the Ekman number is 10 to the minus 15, but we can solve it at 10 to the minus 7. So the question is, can you say something about the hard problem from the dynamics of the easy problem plus a little bit of the hard problem? And this is something that people have looked at. It's called transfer learning. And again, this is work by Anton Pershing. And what you do is you train the ESN on an easy to integrate problem with lots of data. So we go back to our Lorenz system and we train it on something that looks like this. So this would be easy. I mean, okay, imagine this is like horrible 3D PDE, but it's a parameter regime. So we've trained our echo state network. And then you say, well, if I kill myself, okay, so that's just what I showed you before. Of course, I've trained it well. I can predict the statistics. Now you say, okay, imagine that I change rho, and if I kill myself, I can run my model for a very short period of time. So it might be that, you know, I can run my geodynamo at 10 to the minus 4, and if I kill myself, I can run it for a very short time at 10 to the minus 6. So can I say anything about training it on 10 to the minus 4, and then I kill myself to run it for this long at 10 to the minus 6 or whatever. In this case, rho is equal to 32 for the geodynamo, sorry, for the Lorenz system. Sorry, so this is just has a few of these peaks. In fact, it has 1, 2, 3, 4 peaks. This is the map of the peaks. And then you run the neural net forward. So you add in this training to the training you've done before. Can you get the statistics right for that more difficult problem? And it does seem as though, at least in certain circumstances, you can. So the question then is, how much data is needed? And it works very well on a very nice problem like the Lorenz system. We're currently looking at systems with slow, fast dynamics. These are sometimes called reaction diffusion systems. So there's a nice parameter epsilon, which makes your model harder and harder to integrate. And it's a separation of timescales, the so-called Belousov-Zhabotinsky reaction. But ideally, we'd like to do this for the geodynamo. Can you say anything about the statistics of the hard problem by training on the easy problem and putting in a kind of dash of the hard problem a bit later on? So come to my conclusions. So the geodynamo has a very interesting mathematical structure. It's one of these essentially nonlinear dynamos, has much in common with transition and wall-bounded shear flows. ESNs are capable of predicting dynamics they have not seen, but you have to give it something that looks perhaps a little bit like something it might see in the future. And this is interesting, and I'd like to try and understand this a bit more. We've somehow learned something about the full attractor, even from just solving for part of it. There are efficient ways of reconstructing reduced equation sets from data. These are much better if you know some physics. I wouldn't recommend just doing these just straight data science. Okay, I didn't say anything about that. There might be a way of getting to the statistics of a hard to integrate problem by solving an easy one and then using transfer learning. So thank you for your attention.
Okay, questions. I'm sure we'll have many. DM.
In the end, those nets, they're always an interpolation.
Yeah, that's all it is.
So since you're never able to run the DNS at minus 15,
Yeah.
What's for you the best idea? You predict the base state, the flow state at much relaxed Ekman, and then you plug in the correct induction. And you see how that goes.
So there's two interesting ways you could go. I mean, you might be able to run very hard problems for not very long. Computationally, that might be a possibility. So that's a kind of transfer learning type thing. The other thing you might think of doing is not so much an interpolation as an extrapolation. So maybe you've done your you've trained your neural net at Reynolds, or your reservoir network at Reynolds number 200, and then you've trained it at Reynolds number 300, and you've trained it at Reynolds number 400. What happens if you extrapolate the weights? And that's why I kind of like the linear, the linear fitting, because I believe extrapolation might work better. To say Reynolds number 600, does that work or does it not? It's something we're looking into, and it seems to kind of depend. So the question, I mean, obviously you never get something for nothing. You're always throwing away something, but the thing is you can run these things very quickly. And so the other idea is to possibly use these for scales that you can't resolve, and then feed the dynamics of those into a larger scale solver, because they run very quickly.
Weather forecasting has been a big business for a long time, trying to incorporate data into weather prediction. They have to do it on a daily basis. In fact, say that the most expensive stage of weather forecasting is actually incorporating data simulation.
Yeah.
What relation is machine learning to data simulation that exists currently that's used by people?
Yeah, so there are some people who are trying to combine machine learning with data assimilation. I mean, the data assimilation I know about are so-called ensemble methods, and I think they are possible to combine with machine learning. So that's what's called sequential data assimilation rather than variational data assimilation. Yeah, I think, being honest, I don't think there has been much progress, but perhaps that there might be some in the future. Yeah, it's interesting because there's a question is like, how much information should you be getting from your observations versus how much should you be getting from your model? If you're the Met Office, you don't want to run this really incredibly expensive model, but take all your information from your data. Vice versa, if you don't want to just run the model and then not give any weight to the data. So the question then is how much, what's the best thing for prediction? How much of one and the other should you take? And the Met Office seem to think 80% for the model, 20% for the data. That's their ballpark.
So if I rephrase what you said, is it the same as saying that if you had perfect data, you wouldn't need the model at all? If you had a perfect model, you would need the data.
Absolutely. So with the current state, they think 80% of the information should come from the model.
For the two-dimensional magnitude convection,
Yeah.
So the way I understood you made a POD, whatever, and then retain a finite number of modes.
Yeah.
Getting a reduced model that you retrain with your system and trying to recover the original reduced model. I was wondering whether by adding a few other modes, you might explore a broader or finer meeting of the phase space, and then reducing in a sense the possibility for the automatic system to find a model.
Yeah. That's
independent of the number of the modes.
That's a very interesting question. It's one we're looking at. So if we take if you go back, if you take the system we looked at, okay, let's just take this. This isn't quite for the moment, but for this system, you can see that this is really is well described by these modes, right? Now, if you wanted to push that into a different parameter regime, you might say, well, that's not going to be a very good model because these modes here might come up. So, is there any benefit to taking these anyway? That's really your question, and then trying to do the regression against those. The problem is these will have very little power, and so they'll, well, not for us, but they're more likely to be corrupted by, sorry, can you see Pat's in the way? They're more likely to be corrupted by noise, so that these are more likely to, be kind of hard to do the regression for. So yeah, it's something we're looking at, but I didn't want to minimize, but denoising is really a serious problem for some of these things, because you're essentially regressing a derivative against the functions, right? Which is why, okay, I should go back and give these guys credit. I think, okay, the paper by Alves and Fuser that I showed, they did integrations. So they did a weak form of the solution to try and get rid of some of the noise from their PIC simulations. So that, I thought that was a very interesting idea. So essentially they came up with integral forms of the equation. Yeah.
All right, we'll go Xavier first and then Norman next. Okay.
Well, going back to the excursions, you
Yeah.
mentioned that it's maybe related to some physics related to the output. So the question is, are there precursors that could actually help constrain the models coming from wave propagations?
I mean, the information we have about these excursions is really essentially what I put up. Let me just, sorry, going all the way back to the. I'm sure there's a quicker way of doing this, but sorry, we'll get there in the end. So, talk to yourself for a minute. So, okay, there's Reynolds. Oh, well, okay, so we're close. There's the sun. Here we go, sorry. Okay, it's really this. I mean, so we have information about excursions essentially from, I mean, this is an incredibly hard thing to do. You're trying to work out where the pole of a dipole is based on taking, measurements, from around the world. And so we have, I mean, there is, there's no understanding of why sometimes the pole does this versus why it does this. I think it's fair to say. What does seem to be clear is that what's happening is the dipole seems to be going to zero, and higher order, octopoles and quadrupoles and octopoles are coming in. And so it's really just a cartoon model that says, imagine you've gone to sorry, what did yeah, imagine you somehow managed to get the field here really, the dipole field here really small. But the residual dipole field in here is not really small. So in order to get a full reversal, you need to somehow reverse both of these fields. Otherwise, this thing's going to go small, and then this one's going to influence it back, and it's just going to go back round to where you started. But that's, I don't think, I wouldn't say that's established.
So essentially, B field, but there is no information on the flow. So.
No, so people do try and work out something to do with the flow. So what you can do is you can extrapolate the field back to the core mantle boundary, because knowing it's a potential field in the mantle. But then in order to make some assumption about what the flow is doing in here, you really need to make some assumptions, because you can only, you see certain components of the field. So there's a whole literature in trying to make assumptions about what the flow is. And we have good estimates about the strength of the flow, perhaps, just by from knowing about what's called the westward drift, how things, magnetic fields moving currently. But we really don't know very much about the flow inside the fluid outer core. We know more about the flow in the sun. Yeah.
Norman, you still awake back there?
So you mentioned that I guess, and you mentioned that you have actually so it doesn't really work.
Yeah.
Is that a property of the underlying system, or is that a property of the system of the system?
Yeah. So the question for those people who are listening was, it was hard for us to use it as an early warning system. Is that a property of the echo state network as an early warning system, or of the actual dynamics? I'll be honest, I don't really know, but if I were to guess, I would say it's of the dynamics. I think it depends probably on this dynamics here, like your kind of what is the dynamics? If it's a very strongly the Lyapunov exponent transfers, that's very positive. You might get shot out, before, even if very much out of that. I think it could be system dependent, but I think to answer the question honestly, I don't know. It's really interesting.
The beginning of the training, how much of all these techniques are sensitive to noise with the Wedgman data?
So the question was, how much are these techniques sensitive to noise?
Yeah.
So the Cindy one, the second one, I think it is sensitive to noise, and so there's a lot of research into how to minimize the effects of noise. The first one, I think less sensitive. Somehow the echo state network manages to average over the effects of noise. We haven't systematically added noise, but that would be an interesting thing to do. Yeah.
Okay, let me ask a question while you made is a physics question actually, not about machine learning, but you drew parallel between pipe flow and the nonlinear dynamo.
Yeah.
In pipe flow, I mean, really, the signature of the onset is this idea of puffs,
Yeah.
which overlap by directed percolation
Oh,
and
wow.
all of this. And
Yeah.
can you elaborate a little on that?
Okay, I would be very surprised if any theories of directed percolation went through to the dynamo. So
What I would think.
you can push analogies too far. So I think this whole idea of puff splitting and directed percolation and having this kind of I'm not certain any of that goes through to the dynamo. But I think
then what is the basis of the analogy?
the basis of the analogy is really just that there's a lot. If I draw it again, I'll try and find it. You have a state which goes unstable, and then you have a strongly subcritical state, And this is like a, age of chaos. This is a complicated state. Splits the two, and sometimes you might come to there, sometimes you might come down to here. If you're over here, you might hang around here for a while, maybe you'll leave.
All right, in other words, the similarity is some sort of S curve.
Yeah.
Okay.
Yeah.
But I mean,
But
that's
also
not a very distinctive.
But also, okay, slightly more than that. This is a complicated attractor, a complicated state. Yeah.
Looks like. All right, one last question for the Legionnaire, and then coffee.
Cindy, one of the difficult points afterwards is that after you apply the method is to interpret the method.
Yeah.
So when you think about the full system, you have Navier-Stokes and cross induction, etc. A very sensible choice of operators is to actually keep the operators from the Navier-Stokes themselves.
Yeah.
Itself. So you might end up just having your computer telling you what you already know, it's math or that or whatever. And if you project on the different ways of operators, well, you can't interpret anything. So do you have a way in which you see a smart way to deal with that?
Okay, but I think what I want to stress is that this is for physicists to work out. I mean, we shouldn't throw away the physics. We spent lifetimes trying to understand physics, and just because we have some things from data means we don't just kind of throw away all our understanding of physics. So wait for Robin's talk next week. They identified, or Pat can speak better than me, they identified, not using Cindy, but using another term in the transport that perhaps you wouldn't have thought was the key term. But then once they've got it, then as physicists, they can understand it and explain it. And so that, I think, is, otherwise the data scientists are just going to take over the world, and we don't want that. So we need something for physicists. And that, I think, is key. I mean, we can't throw away the physics.
Well, at the thought of the data scientists taking over the world, I think, we don't really need Cambridge Analytica.
No, we don't. No.
So let's thank Steve again, and your neural nets can recover the way to coffee. Thank you, sir.